In today's video, we're going to look at the sum, difference, double and half angle formulas. This is just figuring out some formulas where we can look at sine of the sum of two angles, cosine of the sum of two angles, tan of the sum of two angles. Same with the subtraction of two angles. Then we can look at what is sine, cosine and tangent of 2 times an angle, and what is sine, cosine and tangent of 1/2 of an angle. Okay, there are formulas for all of these and they can all be derived. I'm going to show you one of these formulas. Some of them are easier to derive than others. I'm going to show you one which is going to kind of incorporate one of these sum and difference formulas. And from there on out, the double and half angle formulas can be pretty easy to derive. You don't need to remember these derivations at all, don't remember the proofs. It's just kind of to help you along to see where they come from, so that you're not just blindly being given some formulas. You do need to remember these. I'm going to do a bunch of different examples to go through different types of problems that you may come across, but they can be very useful in especially trying to figure out some trigonometric functions of angles that you may not be able to have found before. Okay, maybe they don't have a reference angle that is easy to figure out and therefore easy to find the trigonometric function of that angle. So they can be pretty useful. First thing I'm going to look at is these sum and difference formulas. So you'll see for two different angles, A and B, it gives us what sine, cosine and tangent of the sum of the two angles are in terms of sine and cosine, and for tan it's just in terms of tan. And same for if I take two angles and I subtract them, what sine, cosine and tangent of those angles subtracted from one another. Okay, it's not just as simple as sine of A minus B is sine A minus sine B. There is more to it than that. So you will need to remember these formulas like I said. And they can be pretty useful. Most of them, once you've remembered one, it's pretty easy to remember the others. But yes, you will have to commit these to memory. I'm going to look at deriving the cosine formulas. The sine formulas follow on very much the same way that these cosine formulas do. So you can go ahead and try those. And then the tan formulas are found by just taking sine of A plus B divided by cosine of A plus B. So it's found by taking this formula divided by this formula and then just doing some manipulation with division. Okay, so you take that fraction of the two different formulas and then you're just going to do some manipulation. But that one's not difficult to actually derive. But we are going to look at these cosine formulas. I will come back to the double and half angle formulas in a bit. But we're going to look at proving that cosine of two angles added together is equal to cosine of one angle times cosine of another angle minus sine of the angle, sine of the other angle. Okay. How do we do this? Well, these pictures came out of the textbook and they're really good at showing you exactly what you need to do. We've taken two angles, alpha and beta, and we've drawn them on the unit circle. So we have this angle beta that has that terminal side, that the coordinate of the point on the unit circle where the terminal side lands is that P1. So that's going to have xy coordinates, cosine beta and sine beta. So cosine beta is going to be the x coordinate of that terminal side on the unit circle, and sine beta is going to be the y coordinate. We do the same thing for the angle alpha. Okay, so we figured out that its xy coordinates on the unit circle for that terminal side are going to be cosine alpha and sine alpha. Then I have this angle here, which is alpha minus beta. Okay, so it's our bigger angle alpha minus that smaller angle beta. And then I've made a triangle out of this. So that straight line that is opposite that angle alpha minus beta, I've made that a third side to create this triangle here. Okay. I know it looks very much like it, but alpha minus beta is not necessarily 90 degrees. I know it looks very close to it here, but it is not necessarily 90 degrees. It is just that we have made this isosceles triangle. We already know that both of these distances would be 1, and then we've got this distance that we'll call D here. Okay, so we've just got this triangle. Then what I'm going to do is I'm going to rotate that triangle around. So now the terminal side for that angle of beta is now going to sit on that x-axis. So I'm just taking my original triangle and I'm just going to turn it around. Okay. Now I have this terminal side here for an angle alpha minus beta. Because we are now in standard position for the angle alpha minus beta, that tells me that the coordinates of the point on the unit circle here, where I've drawn this dot, the coordinates of that dot are going to be cosine of alpha minus beta and sine of alpha minus beta, because that is where the terminal side lands on the unit circle. Okay. And now where we did have that terminal side for the angle beta, that is now going to sit on the x-axis. So the point where it hits the unit circle is now going to be 1, 0, okay, because we have a length of 1 as it's a unit circle and it's on the x-axis, so it's got a y-coordinate of 0. Now I'm going to bring in the distance formula. So the distance between 2 points, x1, y1 and x2, y2, the straight line distance between those 2 points in the plane can be given by this formula here. I'm going to use that 2 different times. First, I'm going to use it on our first circle here. So I'm going to take my points x1, y1 and x2, y2. I've taken my point x1, y1 to be cosine alpha, sine alpha, and my point x2, y2 to be cosine beta, sine beta. So this actually ends up being x1, y1. This one ends up being x2, y2. What I've done in this distance formula, I've actually subtracted the y's first and squared it, and then subtracting the x coordinates and squaring it. It doesn't matter which way around, it's just an addition here. So that's what I've done here. I've plugged in the points cosine alpha, sine alpha, and cosine beta, sine beta into my distance formula. Because all I have done in this second image here is turn the triangle around, this distance here is still exactly the same as my distance on the original triangle. I've just taken my original triangle and rotated it. So those distances must be the same. So I'm going to use that distance formula again. I've taken my 2 y coordinates and subtracted them and squared it, and taken my 2 x coordinates, subtracted them and squared it. And then I know, because it's the same triangle, these 2 distances must be exactly the same. So you can set them equal to one another. So you set them equal, and because they're both under a square root, I'm going to square both sides to simplify it. And then we're just going to multiply the whole thing out, because we've got sine alpha minus sine beta squared. So I'm going to square that parenthesis to get sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. You do the same thing for the cosines here. You're going to square that parenthesis here. And then you do the same thing on your right hand side. You just multiply it all out. Okay, so we're getting rid of those parentheses squared. And this leaves you with what we have down here, which looks like a total mess. So we need to tidy this up. How do I do that? Well, using the Pythagorean theorem, I know that sine squared of an angle plus cosine squared of the same angle equals 1. So that tells me here I've got sine squared alpha plus cosine squared alpha. That must equal 1. I've got sine squared beta plus cosine squared beta. That must equal 1. I've got sine squared of alpha minus beta plus cosine squared of alpha minus beta. That must also equal 1. So I've got a bunch of terms here that when added together I get 1. So I should end up on my left hand side, I get 1 plus 1 minus this term minus this term. Okay. And then on my right hand side I get 1, I've got another 1 here, so that's 2 minus 2 cosine alpha minus beta. I can cancel out the 2's and then divide by negative 2, and that leaves me with what I have here. That is just the difference formula for cosine. Cosine of one angle minus another angle is going to equal sine of each of the angles multiplied together plus cosine of each of the angles multiplied together. Okay. Then, in order to get that sum formula for cosine, all I'm going to do is do a quick substitution. I'm going to set b equal to negative beta and a equal to alpha. Okay. So I would end up with sine a sine negative b plus cosine a cosine negative b. When you get sine of negative b, okay, I want to relate that to sine of b. Okay. When you take an angle, let's say pi over 3, okay, sine of pi over 3. Sine of negative pi over 3 is exactly negative of the sine of pi over 3. That is the same with any angle. If you start out with an original angle and you take sine of it, and then you look at sine of negative of that angle, they are just negatives of one another. It's because you are flipping that angle effectively in the x-axis. So your y-coordinate becomes negative, hence the sine of that angle becomes negative. Okay. Alternatively, cosine of negative b actually just equals cosine of b. Cosine is the x-coordinate. When you take negative of an angle, the x-coordinate does not change. Okay, the x-coordinate of that terminal side does not change. It's only the y-coordinate that changes. So cosine of negative of an angle equals cosine of the original angle because it does not change the sign of that x-coordinate, hence it doesn't change the sign of cosine. So when you put that all together, you end up with cosine of a plus b is going to be cosine a times cosine b minus sine a sine b. So that's where this comes from. So let me come back to our difference formulas and sum formulas. We've looked at where cosine a plus b and cosine a minus b comes from. Like I said, it's a very similar way in order to find and how to derive sine of a plus b and sine of a minus b. And then tan of a plus b and tan of a minus b is just found by taking our formulas for sine of a plus b divided by cosine of a plus b. For tan of a minus b, it would be sine of a minus b over cosine a minus b. And then you're just going to manipulate those fractions and you will end up with those tan formulas. How about the double angle formulas? Where do they come from? They actually are derived from the sum formulas. Okay. If I come back to my sum formulas here, let's look at sine of a plus b. If I make sine of a plus b sine of a plus a, so I'm making b equal to a here. If I have sine of a plus a, that would give me sine a cosine a plus cosine a sine a. Okay. That's just the same thing added together. Okay, I get sine a cosine a plus sine a cosine a. That's 2 sine a cosine a, which is exactly what the double angle formula is. So you can find these double angle formulas just by setting a is equal to b in each of these formulas and then simplifying them. Where do my half angle formulas come from? Well, they actually come from this double angle formula that we have here for cosine. Okay. If I set a is equal to b over 2, okay, let's say I'm looking for this half angle formula. I would get cosine of b over 2 multiplied by 2, okay, so 2 times a, is equal to 1 minus 2 sine squared of b over 2. Okay, that leaves me with cosine of b is equal to 1 minus 2 sine squared b over 2. And then if I rearrange this for sine of b over 2, I end up with this formula here. Okay, because I would get sine of b over 2 is equal to plus or minus the square root of 1 minus cosine b divided by 2. Okay. Okay. So that's where they come from, is they come from that double angle formula and just setting A is equal to a half of a different angle. Okay. Now that we have all of these formulas, I'm going to go through several examples of using these so that you can see where they are going to crop up. Okay. First one that I want to look at is going to be sine of 105 degrees. Okay, I'm going to start out in degrees. It turns out that 105 degrees is the same thing as saying 45 degrees plus 60 degrees. Now I know all about sine and cosine of 45 degrees and 60 degrees. So because I have this angle that is the sum of two different angles that I know a lot about in terms of trig functions, I can just go ahead and use the sum formula for sine. So sine of two angles added together is sine of the first angle, cosine of the second angle, plus sine of the second angle, cosine of the first angle. Okay, so I'm just using that sum formula for sine. That's going to give me the square root of 2 over 2 multiplied by 1/2 plus the square root of 3 over 2 multiplied by the square root of 2 over 2. If you simplify that, you get the square root of 2 over 4 plus the square root of 6 over 4, and then you can make it into one fraction as you have that common denominator. Okay. So I could find sine of this random angle because it is the sum of two angles that I know a lot about. Okay. Do the same thing this time using a tan formula. So I'm going to look at tan of 75 degrees. Okay. Again, it's an angle that doesn't have a reference angle that we know a lot about. So therefore I'm going to use the fact that 75 degrees is the same thing as 45 degrees plus 30 degrees. Now I know a lot about those two angles, so I can go ahead and use that sum formula for tan and figure out what tan of 75 degrees is. So it's going to be tan of the first angle plus tan of the second angle divided by 1 minus tan of the first angle, tan of the second angle. Okay. Like I said, you're going to have to commit these different formulas to memory. I know that some of them aren't that easy to remember, but most of them follow a pattern, so you can remember them pretty easily. So that's going to be 1 plus 1 over the square root of 3. Tan of 45 degrees is 1. Tan of 30 degrees is 1 over the square root of 3. Divided by 1 minus 1 times 1 over the square root of 3. Okay. If you go ahead and simplify all this, I'll let you do the simplifying for this, is 3 plus the square root of 3 over 3 minus the square root of 3. Okay, let's go through another one, this time with radians. So I'm going to look at cosine of 11 pi over 12. Okay, again, I want to write this angle as the sum of two angles that I know something about. Okay, so either an angle that is pi over 4, pi over 3, pi over 6, or one that has one of those angles as a reference angle. Turns out that 11 pi over 12 would be 3 pi over 4 plus pi over 6. So I can use that cosine sum formula in order to find what cosine of 11 pi over 12 is. So it will be cosine of 3 pi over 4, cosine of pi over 6, minus sine of 3 pi over 4, sine of pi over 6. Now you can get these values from the unit circle. Cosine of 3 pi over 4, that's in quadrant 2. And we are looking at, in quadrant 2, the angle that has the reference angle of pi over 4. So cosine of 3 pi over 4 is actually going to be negative the square root of 2 over 2. Cosine of pi over 6 is the square root of 3 over 2. Sine of 3 pi over 4 is the square root of 2 over 2. And sine of pi over 6 is 1/2. So if you put all of that together, you get negative the square root of 6 over 4 minus the square root of 2 over 4. And then you can combine those into one fraction. So we're going to have negative the square root of 6 minus the square root of 2 all over 4. Going back to degrees, let's look at one that now has a negative angle in it. So I want to find negative 75 degrees as the sum or the difference of two angles that I know something about. Okay. The breakdown, and 9 times out of 10, unless it was really obvious what the breakdown was, I would give you what the breakdown was. Unless it's really obvious when you add two very obvious angles together what that would be. It turns out that negative 75 degrees would be 45 degrees minus 120 degrees. Okay. We definitely know something about 45 degree angles and sine and cosine of those. For 120 degrees, that is an angle that is in quadrant 2 that has a reference angle of 60 degrees. So we do know something about 120 degrees. You may not see it at first, but if you look at our unit circle, it is just the angle in quadrant 2 that has the reference angle of 60 degrees. So we're going to use our sine difference formula here, which would be sine of the first angle cosine of the second angle minus sine of the second angle cosine of the first angle. And now you can just fill this in from what we know from the unit circle. So sine of 45 degrees is the square root of 2 over 2. Cosine of 120 degrees. Okay. Well, cosine of 60 degrees is 1/2. But now we are in quadrant 2. So for 120 degrees, because it has that reference angle of 60 degrees, but we are in quadrant 2, making cosine negative, it makes the x coordinate on the unit circle negative. It's going to be negative 1/2. Minus sine of 120 degrees, okay, it's going to have that same y coordinate as 60 degrees, so sine of 60 degrees and sine of 120 degrees, they're going to be the same value. And then cosine of 45 degrees is square root of 2 over 2. And then you can simplify this, it would be negative the square root of 2 minus the square root of 6 over 4. Something a little bit different now. I'm going to look at cotangent of negative pi over 12. Okay. Cotangent, if you remember, is just the reciprocal of tan. So now I'm looking at tan of negative pi over 12, and then I take its reciprocal. Let's first look at tan of negative pi over 12. I've got to write negative pi over 12 as the sum or difference of two angles that I know something about. Okay. Negative pi over 12 is actually pi over 6 minus pi over 4, and I definitely know something about those two angles. Okay. So that would be the tan difference formula, which is tan of the first angle minus tan of the second angle divided by 1 plus tan of the first angle, tan of the second angle. Now, if you don't have a calculator in front of you, all you have to do to figure out tan of each of the angles is just to do sine of the angle divided by cosine of the angle. Okay? So if you do that the whole way along, and I know that that can be kind of tedious, especially if you don't have a calculator, but once you've done all of that, you should end up with the square root of 3 minus 1 over 1 plus the square root of 3. So the reciprocal of that would be cotangent of negative pi over 12. So the cotangent of negative pi over 12 is going to be 1 plus square root of 3 over the square root of 3 minus 1. So like I said, with this kind of problem, especially with tan, I would use a calculator, even if it's just to double check. But if you didn't have a calculator for this, for each of those tan values, you're going to do, let's say you've got tan of pi over 6, you're going to figure out sine of pi over 6 divided by cosine of pi over 6. And you would do the same thing for pi over 4, and then you could go ahead and fill this in. Now let's look at using a double angle formula. So this time I'm going to look at sine of 450 degrees. Now I'm going to do this using the sine double angle formula. So this would be sine of 2 multiplied by 225 degrees. Okay. So using the double angle formula for sine, that would be 2 sine 225 cosine 225. Okay. 225 degrees, where is that? It's 45 degrees past 180. Okay, it has a reference angle of 45 degrees and it is in quadrant 3. So we do know a lot about 225 degrees. Okay, so it has that reference angle of 45 degrees, it's in quadrant 3. That means that both the x and the y coordinates are negative, so sine and cosine are both negative. So it's square root of 2 over 2 and negative the square root of 2 over 2. Okay, which would be 2, then the negatives cancel, square root of 2 times square root of 2 is 2, 2 times 2 is 4. So that would give me 4 over 4, which is 1. So sine of 450 degrees, using that double angle formula, we find out that it is 1. How about, again using the double angle formula, we're going to look at cosine of 300 degrees. Okay. So that would be cosine of 2 multiplied by 150 degrees. Now there are different versions of that cosine double angle formula. I'm just going to use the first one, which would give me cosine squared of 150 degrees minus sine squared of 150 degrees. 150 degrees, it's in quadrant 2 and has a reference angle of 30 degrees. So because it's in quadrant 2, we know that the x coordinate is going to be negative, the y coordinate would be positive. So that tells me that cosine of 150 degrees is going to be the negative value for whatever cosine of the reference angle is. So that would give me negative the square root of 3 over 2, and then we're squaring that. And then the sine value is going to be positive. So we know that 150 degrees has that reference angle of 30 degrees. Sine of 30 degrees is 1/2, and sine of 150 degrees is going to have that same sign. It's still going to be positive because that y coordinate on the unit circle is positive. So when you simplify this out, you're going to get 3 over 4 minus 1 over 4, which gives you 1/2. Now I'm going to look at some different types of problems that you may come across. Okay, again, we're going to be using these sum and difference formulas and these double angle formulas in order to solve a different type of problem. Half angle formulas don't come up too often. It's useful to know those half angle formulas, but they very rarely are going to be seen in a lot of the mathematics that we're going to be doing. First problem that I want to look at for this example is to find the exact value of sine of alpha plus beta if I know that sine of alpha is equal to 3 over 5 and I know that alpha lays in quadrant 1. And then cosine of beta is 2 times the square root of 5 over 5. And I know that beta lies in quadrant 4. Okay, so I've got one that lies in quadrant 1, one that lies in quadrant 4. And the question is, what is sine of alpha plus beta? Now I know from my formula, sine of alpha plus beta is equal to sine alpha cosine beta plus sine beta cosine alpha. So my issue is I don't know cosine of alpha and I don't know sine of beta. So they're the two things that I need to find. The way I'm going to do this is by using some right angle trigonometry. So first looking at the angle alpha. The alpha there. I know that sine of alpha is 3 over 5. If you go back to our right angle trigonometry and use that SOHCAHTOA rule, you know that sine of an angle is opposite over hypotenuse. So I'm going to set the opposite to alpha as 3 and the hypotenuse as 5. I've just got to find this side here, so I can go ahead and use Pythagoras in order to find that. So that would give me x squared is equal to 5 squared, which is 25, minus 3 squared, which is 9. So 25 minus 9 gives me 16. So x is equal to plus or minus 4. Okay. Question is it plus or minus? Well, we know that alpha is in quadrant 1. In quadrant 1, both sine and cosine of any of those angles are both positive. So I know that cosine is going to be positive, so I'm going to take the positive value of my unknown. Okay. So that tells me that cosine of alpha, which is adjacent divided by hypotenuse, is going to be 4 over 5. I'm going to do the same thing with beta. Again, I'm going to draw a triangle with my angle beta. Now I know from my problem here that cosine of beta is 2 the square root of 5 over 5. Cosine of an angle is adjacent divided by hypotenuse. So adjacent is 2 the square root of 5 divided by 5, which is my hypotenuse. And I've got to find my unknown. Again, I use Pythagoras, so I'm going to get 2 the square root of 5 squared plus my unknown squared is equal to the hypotenuse squared. 2 times the square root of 5 squared is going to be 20 plus my unknown squared. So x is going to equal plus or minus the square root of 5. Again, I need to figure out if it's the positive or the negative. Now, I'm told that beta is in quadrant 4. In quadrant 4, cosine is positive, sine is negative, because the x coordinates are positive, the y coordinates are negative. So now I know for my sine of beta, it has to be negative because we're in quadrant 4. Beta lands in quadrant 4. So I know that I'm looking at the negative. So it's going to be negative square root of 5, which is the opposite, divided by the hypotenuse. Now we can plug everything in. So sine of alpha plus beta is going to be sine of alpha times cosine beta, so they're the two things that we were given originally. So 3 over 5 multiplied by 2 the square root of 5 over 5 plus sine of beta, which is negative the square root of 5 over 5, multiplied by cosine of alpha, which was 4 over 5. If you go ahead and multiply all of this together and simplify it down, you should end up with 2 times the square root of 5 over 25. So this is the other type of problem that you might get, where you are given some values of sine or cosine of the angles, and you have to figure out the value of sine or cosine of the sum or difference of the angles. We can also do this for double angle formulas. So the other example that I'm going to look at is to find the exact value of sine 2 theta, where sine of theta is going to equal 7 over 9, and I'm going to set theta to be in quadrant 2. Okay. Now, same idea again. I know that sine of 2 theta is equal to 2 sine theta cosine theta. I have sine of theta, I don't yet have cosine of theta. So I need to go ahead and draw a triangle in order to figure out what cosine of theta might be. So sine of theta is opposite divided by hypotenuse. So my opposite is 7, my hypotenuse is 9. I need to figure out my unknown. So that would be 7 squared plus x squared is equal to 9 squared. So x squared would be 81 minus 49, which would be 32. So x is going to be plus or minus the square root of 32. Is it positive or negative? Well, we know that theta lands in quadrant 2. Cosine of any angle in quadrant 2 is negative because the x-coordinate of that terminal side of the angle is going to be negative. So I know I am looking at negative the square root of 32. So sine of 2 theta is going to equal 2 multiplied by sine of theta, which we already had as 7 over 9, multiplied by cosine of theta. So cosine of theta is going to be adjacent divided by hypotenuse. The adjacent we said was negative square root of 32, hypotenuse was 9. So if you multiply that together, you would get negative 14 times the square root of 32 over 81.